So we started talking about the central limit theorem. And the central limit theorem said three things. It said under certain conditions, the mean of the sample means is normally distributed. And exactly what it says is as your sample sizes increase, your distribution gets closer to normal. And we said as long as it's over 30, you're okay. And as long as, I don't know if we said that or not in class, we'll say it now. If your sample size is at least 30, that's big enough. Okay. Second thing it said is the mean of those two distributions are the same. The population mean that you start with is the same as the population mean of all the sample means that you take. So those means are the same. And the standard deviations are not the same, but they're related, and you can relate them with this formula. So this is the first thing. The mean of all the sample means is equal to the original population mean that you started with, your original population's mean. And the standard deviation of those sample means has a formula that uses the standard deviation of the original population. So they're related. If the sample means are normally distributed, that means we can use the normal calculator to calculate probabilities about means, about sample means. But to use the calculator, we need that distribution's mean and standard deviation so we can plug those in the calculator. Well, this is what we're going to do to find those. Okay? We need those two to put in the calculator, and we'll get we'll get our distribution and be able to use it. So the distribution of the sample means will, as the sample size increases, approach a normal distribution. So another way to write this will say as n gets bigger, as n approaches infinity, x bar will approach a normal distribution. The distribution of all the x bars will approach a normal distribution. They'll get closer to normal. If the population does not have a normal distribution, then we must have a sample size greater than 30. So how big does n have to be in order for us to go ahead and call it normal and use the normal calculator? We're going to say 30. Now, you can get by with less than 30, but 30 is the safe number. Okay? So you can get normal-looking bell-shaped distributions with less than 30, but we want to be guaranteed that the areas that we're calculating are going to be correct to like 4 decimal places. Okay, so that's why we use 30. So we're going to make it a strict thing where we know that our areas are going to be correct. Okay. If the original population has a normal distribution already, then it really doesn't matter how big a sample size you take. You automatically get normally distributed. Sample means. So we need one of these two. We need either the sample size is bigger than 30, or we need the original population to be normal already. And if it is, then we automatically get normality in the sample means. Okay, so let's actually do some problems. So this says a random sample of size 54 is obtained with a population with mean 80 and standard deviation 14. Describe the sampling distribution of x bar. So what does it mean by sampling distribution of x bar? What that means is you take every possible sample of size 54 and graph the distribution. That would be the sampling distribution of x bar. So we're asking, what's the distribution of all the sample means? What does it look like? We're going to describe it. So describe it for me. What shape does it have? We know that we're taking samples of size 54, right? We only took this one sample. We're going to imagine if we took every possible sample of size 54, then they would be normally distributed. The sample means would be normally distributed of all those samples because it's bigger than 30. So we know that it's normally distributed. We don't have to take all those samples. We're just going to imagine if we did, and we took all the sample means, then it would be normally distributed. And we know the mean of that distribution, and we know the standard deviation. So part of the describing is what's the mean. So the mean of the sample means is exactly the same as the original population's mean. And we know the standard deviation. It's not the same, but we can use the information we have to find it. So that's the standard deviation of that distribution. So the population mean is 80. The population standard deviation is 14. And we're asked to find what's the probability that X bar is greater than 83. So we're saying if you take a simple random sample of size 54 from that population, what's the probability that the sample mean that you get of this 54 will be greater than 83? So because it's normally distributed, I can use that StatCrunch calculator. And I know its mean and standard deviation, so I'm going to plug those into the calculator. Okay? So we need StatCrunch. So if you haven't already, let's open StatCrunch. So I have my normal distribution. I'm going to change the mean to 80. And the standard deviation is 14 over square root of 54. StatCrunch is not going to let us type it in that way. So we're going to find an approximation in the calculator first. So I'm going to say, give me the decimal form of this number. If I can type it in correctly. So I'm going to get a decimal in my calculator, and I'm going to put that in as the standard deviation. Okay. How many decimal places? I'm just going to type them all in. There's no reason not to. It takes about an extra second or two to type the rest. Okay, so our calculator is rounding already to, this looks like 9 decimal places. I'm going to go ahead and type all of those in. And I'm only going to round at the end to 4. I think it'll ask me to round the answer to 4 in the homework. But I'm just going to go ahead and type that entire decimal in for the standard deviation. You could probably get away with less, but why would we risk getting the answer wrong? So this X now is really X bar because I've put in the mean of the sample means and the standard deviation of the sample means. This is the distribution of the sample means now. So this is, what's probably the X bar is greater than 83. And I get this. So 0.0577. So it didn't say anything about our population being normally distributed, but that doesn't matter because our sample means will be normally distributed if we're taking samples, a sample size bigger than 30. So that means we can use that normal calculator. And nothing, this is the same problem we did last chapter, right? In chapter 7, we did this exact same thing. I've just added an extra step. The extra step is we have to change the standard deviation to something else, right? It's got a different spread, but it's got the same center. It's got the same mean, but it's got a different standard deviation. So what's the probability that x bar is less than or equal to 75.8? So I'm just going to change this to less than, and I get 0.0137. And then between, so I'm going to click the between. And again, it's just like all the other problems we did. We just had to change the standard deviation. So 0.8102. To 4 decimals. Are there any questions? It's a hard concept to grasp, I think, but it's very easy to do, right? We can do these problems because they're just like the problems we just did. Okay, they're just about sample means instead of about the actual data, the actual population. Okay, so this says, number 2 says the most famous geyser in the world, Old Faithful in Yellowstone National Park, has a mean time interval between eruptions of 85 minutes. If the interval of time between eruptions is normally distributed with a standard deviation of 21.25 minutes, answer the following questions. What is the probability that a randomly selected time interval between eruptions is longer than 95 minutes? So the length of time between these eruptions is normally distributed, and we know its mean and standard deviation. We could draw that distribution, and x would represent the time intervals between eruptions. You know, how long it takes between 2 eruptions, or consecutive eruptions. And this says, what's the probability that a randomly selected time interval between eruptions? That means we're only picking one. What's the probability that that one is longer than 95 minutes? So this is just x. Does everybody see that? We're picking a randomly selected time interval. This is a Chapter 7 problem. It's normally distributed. I know its mean and standard deviation. I'm just going to type those in to my calculator, and I'm going to find the area to the right of 95. So the mean is 85. The standard deviation is 21.25. And I want area to the right of 95. Just like that. No different than the last chapter. So what's different about B part? So read B part. What's different about that one? Now we're picking 20 of them. Not just one, I'm picking 20 of them. And it's asking about the probability about the mean of those 20. So it says, what's the probability that a random sample of 20 time intervals between eruptions has a mean longer than 95? What's the probability that I take a sample of 20 and the average of those 20 eruptions, or 20 time intervals, is bigger than 95? So this is the probability that x bar is longer than 95. Now we have to use central limit theorem. So I know the mean of those sample means. If I took every possible sample of size 20, I know that the mean is going to be the same. And I know the standard deviation is related with this formula. I'll take the old standard deviation and divide by the square root of the sample size. So the question is, can I do this problem with the normal distribution? Are they normally distributed? Are the sample means normally distributed? So our sample size is 20. That's not bigger than 30. But what? I just said it a few minutes ago. Sorry? There's 20. So that's not bigger than 30. So can we use the normal distribution? The answer is yes. So let's go back. So this says there's two things. You need one of the two. You need a sample size bigger than 30, which we don't have, or if the original population is normally distributed, it doesn't matter how big the sample size is. Okay? So you need one of the two. You either need a sample size bigger than 30, or you need the original population to be normally distributed, which we do have. So it told us that these time intervals are normally distributed. And in fact, if we didn't know that, we couldn't have done A part. Right? On A part, we used that fact that they told us it was normally distributed. We put it in the calculator, the normal calculator. So we can use the normal distribution here because it doesn't matter what sample size we take, the distribution of all the sample means will be normal, even if we're only picking size 1, because that's what we did on A part. This is a sample of size 1, and we'd still use the normal distribution because it was already normal. Okay. All right. So I need to change the standard deviation here, and I don't have to change the mean. The mean's the same. Standard deviation is different. 21.25 divided by square root of 20. And I'm going to type that in for the standard deviation. And I just type the whole thing in. And I get 0.0177. Okay. Any questions before we go on? We got many more parts. What's the probability that a random sample of 30 time intervals between eruptions has a mean longer than 95? So now the sample size is 30. Well, the mean is still 85. It doesn't change. The standard deviation does change. Now we're going to divide by the square root of 30. And we're going to change that number in our calculator, the normal calculator. So I'm going to find out what this standard deviation is in a decimal form. And I'm going to replace my standard deviation in the normal calculator. And again, I just type the whole thing out. So I get 0.0050. So this is still probably the sample mean greater than 95. It's just I'm picking a bigger sample. So I get a different area. Okay, so D says, what effect does increasing the sample size have on the probability? So we started out with sample size 1 on A part, sample size 20 on B part, sample size 30 on C part. So what happened to the probabilities? They decreased. So it decreased. The question is why. So I just want to draw you a picture here to explain why. So here's sample size 1 is just the original distribution like that. And it had a standard deviation of 21.25, right? Well, what happens if you have two distributions with the same mean but different standard deviations? Right? My second standard deviation was about 4.7, so that means it got skinnier, right? So the second one, the sample size 20, looked like this, right? It was skinnier. Had standard deviation 4.7 instead of 21. And then the third one would be even skinnier than that one, right? And we're asking, the mean is 85. Whoops. And we're asking about greater than 95. Okay? So that is the area to the right. On A part, it was this area, and on B part, it's this area. You can see it's lower, right? Because that tail is got smaller because our standard deviation changed. Right? Our standard deviation got smaller. This formula you divide by the square root of n. So the bigger sample size you take, the bigger the denominator is going to be. That means the smaller this calculation is total. So as the sample size gets bigger, this standard deviation gets smaller. And it did, right? It went from 21 to 4.7 to 3.8, I think. So, yeah, 3.888. So that's why. So it's because the standard deviation got smaller, right? Sigma x bar decreased, therefore the tails got smaller. So E says, what might you conclude if a random sample of 30 time intervals between eruptions has a mean longer than 95? So C part tells us the probability that that would happen. I opened this to let some light in, but it let the noise in too. So it might have helped a little bit. I don't know. Okay, so the probability is 0.005 that this would happen. Is that unusual? 0.005, is that unusual? Yes, it's less than 0.05. Right, 5% or less is unusual. This is 0.5%, so definitely unusual, okay? And if you look at it, it's 5 out of 1,000, right? That's in the thousandths place. So 5 out of 1,000 is about 1 every 200, okay? So 1 every 200 is the probability that this would happen. So it's asking you, what would you think if it actually did happen on your first try? So you know it's very, very unlikely for this to happen. What if it did happen the very first try? What would you think? So there's a 1 in 200 chance that you just got that sample, just by random chance, you got this crazy sample that gave you this result. Okay, that you're just unlucky or lucky, however you want to think about it. What's the more likely thing though that's happening? Sorry? That you're wrong, yeah. Or what we're given is wrong. So I like both of those answers. So either we did something wrong, that could be possibility, or maybe what we're given is incorrect. So this probability is based on an assumption that we've made. The assumption is that the mean is 85, right? And the standard deviation is 21.25. So do we know that the mean is 85? This is population mean. So population mean means of all the time intervals between every eruption of Old Faithful and Yellowstone. Do we have all that? We probably have a lot of it, but we don't have it all, right? So what we would think is maybe that number is wrong. Maybe something has changed since we decided that was the number. So how did we decide it was 85? Well, somebody did research and calculated. They took a sample. They couldn't measure every single time interval between the eruptions. They may be measuring all of them now. They may have somebody who measures them now, but we don't have all that data forever, and they had to stop at some point and say, well, what's the mean? We're going to say it's 85 because that's what our data says, right? So maybe something's different now. Maybe something's going on under the ground or something that's causing the mean to not be 85. So this is an important question. This is how we're going to make statistical arguments. This is what we're going to do later in the semester. We're going to say, if we assume this thing is true, and then something really, really unusual happens, we're going to say, well, maybe that thing is not true that we assumed was true. Okay. So what might we conclude? We might conclude that the population mean is actually bigger than 85 because we got one greater than 95, right? And that's very, very unlikely, right? If if you're playing a game let's say you're playing a game of chance against somebody and they just keep beating you over and over and over, but you think that the game should be fair. You should be winning about half of them. Maybe it's a coin flip game. Heads you win, tails they win, but you lose way more than half. Maybe you think, well, maybe that guy's cheating, right? Maybe it's not a fair game. Maybe my assumption that the probability of flipping a coin on heads was 1/2. Maybe it's not. Maybe that guy's really figured out how to flip a coin on tails, and he's taking your money. So, that's the kind of things we're going to think about. We make these assumptions, and then we get these results, and then we actually test it in the real world. Does it work? Okay, and if it doesn't, maybe the assumption's wrong. Okay. All right. On a certain day, suppose there are 22 time intervals for Old Faithful. Treating these 22 eruptions as a random sample, the likelihood that the mean length of time between eruptions exceeds blank minutes is 0.2. So we've got 22 time intervals. That means we need to change our standard deviation again. So we're going to divide our population standard deviation by the square root of 22. And I'm going to put that in. And then it's telling me the probability. So if you ever see likelihood means probability, right? What's the likelihood this thing's going to happen? It's the same thing as saying what's the probability that it will happen. Probability is likelihood. Okay, they're the same thing. So the probability that the mean exceeds blank is 0.2. So, I mean, you can actually write this out in these symbols. That's the probability that the mean length exceeds blank is, that's an equal sign, 0.2. Well, that tells you where to put the information into the calculator, right? So I'm going to put this 0.2 as the probability. And I'm going to say area to the right with that greater than symbol. And it's going to tell me that mean. So the probability that the sample mean would be greater than 88.8 is 0.2. So this blank is 88.8. So that's X bar. That sample mean that we're looking for is 88.8. Any questions? Okay, so we did chapter 8. We don't have a lot of time, but I still want to start chapter 9. I'm just going to give you like a preview, that I won't have to do it on Tuesday when we come back. And I'm going to take control here because we don't need StatCrunch. I'm going to use it. All right, so let's look at IQ scores. So IQ scores are they have a mean of 100, a standard deviation of 15. And I want to know what's the middle 95% of IQ scores. So I put in 0.95 as the area between, and it'll tell us it's between 70.6 and 129.4. Okay, so 95% of all IQs are between 70.6 and 129.4. All right, so that means that if I were to pick a random person, I've got a 95% chance that their IQ is between those two. Do we agree with that? That's what this is all about, right? That question is the basis of all this stuff that we're doing. Okay, well, let's say that I want to take a sample, not just pick one, let's pick 25. So if I pick 25 and I take the average of those 25, what's the middle 95% of that? So what's the middle 25% of the sample means, of the averages? So let's take 15 divided by square root of 25. So that gives us 3. 15 divided by 5. So I'm going to say, what's the middle 95% now? It's 94.1 to 105.9. What happened to those two numbers there? What happened to these two? It was 70.6 to 129.4. Now it's 94.1 to 105.9. What happened? They got closer together. What are they getting closer to? Each other and 100, right? They're getting closer to 100. You know, if I go back and change this to 15, you see the scale here, right? They're tick marking this by 20 now. If I go back to 3, the scale has had to change a lot, right? They're only ticking by 5, and those two numbers got closer together. So this says that if I pick a sample of size 25, if I pick 25 random people, the probability that or I say I have a 95% chance that the average of their IQs will be between 94 and 106. All right? Let's pick a bigger sample size. How about let's pick 100. So that would be 15 divided by 10, which is 3 halves or 1.5. So now my standard deviation is 1.5. So it keeps getting smaller, right? Every time we raise the sample size. So what happened to the interval again? What happened to these two numbers? Closer? Okay, let's pick a bigger sample size. How about 400? So 0.75. So I picked sample size 400. So that's what it looks like when you take a sample of 400. So first or second day of class, we talked about how you don't really know what the population mean is, right? Because you don't have all the population data, but you try to take a sample in such a way that it's representative, and you hope that your sample mean is close to the population mean, right? Well, this tells us about how close it's going to be. So if I take a sample of 400 random people, and let's say that I don't know that the mean IQ is 100, or I have no idea the mean IQ is 100, and I'm trying to figure that out, I have a 95% chance that the sample mean that I get out of those 400, if I take the average IQ of all 400 of those people, I got a 95% chance that that mean will be between 98.5 and 101.5, right? Which is really close to 100. Do we agree? So it'll be close. I won't know exactly what the population mean is, but I'll have a very good idea, right? And if I do this multiple times, we could see where that mean's gonna be about. So let's just see how close we can get it. Let's try 1,000. We'll say 0.5. We'll just round it to 0.5. Whoops. So that says we got a 95% chance that our sample mean will be between 99 and 101, which we're going to get something close to 100 there, right? So that interval is what we would call a confidence interval. So we use this to actually figure out what these population means are. I don't know what the population mean is. I'll take a big sample and find the mean of the sample. And I know that the sample means are normally distributed, so I know how the distribution of those look like. And I can use that sample mean, and we'll actually compute a margin of error, and it'll give me that margin. See, there's a margin of error here, right? It's about 1 point. So I've got a 95% chance of being within 1 of 100, right? Because it goes from 99 to 101. So I've got a 95% chance of being within 1 of 100. So that would be my margin of error would be 1. Okay. So when you see a poll on CNN, it says president's approval rating is 36%. At the top right corner, it'll say minus 2% or plus or minus 5%. They're giving you that margin of error. They're telling you, this thing's normally distributed. We didn't ask everybody their opinion of the president. But we did ask a sample, and this is our mean of our sample, or this is the proportion of our sample that said we approve of the president. But we're going to tell you this margin of error that lets you know, we could be off by as much as 5% or 2%. So if we took a random sample of 1,000 people, we're 95% sure that we'll be within 1 of that actual population mean, 1 of 100. Okay. Now, what does the 95% mean? Well, the 95% means we can't be 100% sure that that's the case. That means if we did this 100 times, 5 out of 100 about would be wrong. You wouldn't be within 1 of 100. Only about 95 out of 100, or that's about 19 out of 20. Okay. So 19 out of every 20 of these samples will have a mean really close to 100, within 1. About 1 out of every 20, just by random chance, you'll pick this wild sample that's not representative. Okay, because you're picking randomly. There's chance involved. Just by random chance, you might pick a bunch of smart people, and it'll pull that mean up, over 100 or something like that. Okay? All right. So that's what we're going to do next week. So I'm out of time. About the home.